Latent space imaging introduces a new paradigm for artificial vision systems inspired by biological vision. While conventional imaging systems are based on brute force sampling of scene information on regular grids, our human visual system performs significant data reduction from the large number of photoreceptors to the optic nerve, effectively encoding visual information into a low bandwidth latent space representation for brain processing. The concept of latent space in deep learning has driven major advancements across various fields. CLIP, for example, aligns the latent space of images and text, enabling powerful cross-model understanding. Latent diffuse, similarly, leverages a compressed latent space to perform denoising more efficiently, accelerating image generation and serving as the foundation for many modern generative models. In this work, we extend the concept of latent space to cameras and artificial vision systems. We propose leveraging the recent trend of co-designing optical elements alongside with reconstruction neural networks to directly encode information into the latent space. However, since implementing nonlinear operations optically is impractical, we incorporate an additional digital encoder. By jointly designing the optical and digital components to align with the latent space, we significantly reduce the amount of sensor data required for domain-specific imaging, with compression ratios ranging from 100 to 1000 times, and capable of achieving 16,000 times for downstream tasks like face segmentation and landmarks detection. Now, let's dive into the details of the latent space imaging pipeline. The optical encoder embeds the image signal into a compressed set of measurements, called intermediate latent. This is performed by a matrix multiplication with binary optimized patterns. Then the digital encoder, a lightweight neural network, enriches the signal by modeling the nonlinear operations needed to match the latent space of a frozen generative model, enabling image reconstruction. The reconstructed latent can be linearly projected to perform downstream tasks directly, such as facial segmentation, landmark detection, and attribute classification, without requiring the image reconstruction or a complex new model. To physically implement the LSI framework, we need to realize the optimized patterns to modulate the incoming signal. In this work, we prototype using the single pixel imaging pipeline. An objective lens focuses the image onto a digital micromirror device, DMD, which flips its micromirrors to reflect light according to a learned mask, spatially modulating the incoming facial image. This modulated light is then directed through a relay lens, which focuses into a photodiode, SPD, that integrates the signal. Utilizing time multiplexing, we can finally retrieve the necessary measurements. Here, we demonstrate the robust identity preservation capability of our model when reconstructing images at a resolution of 256 times 256 across a range of compression levels. LSI effectively captures essential features such as eye color, expression, facial shape, and skin tone with less than 0.5 of the original pixel count. The similarity declines after 2048 times compression, however, is still accurate for downstream applications. As we can observe, the accuracy for attribute classification, landmark detection, and face segmentation maintained good even for the same 2048 times less measurements. Both the current results and the previous downstream tasks are based on real-world signals acquired using our prototype, highlighting the physical realization of the proposed method. Finally, latent space imaging presents a powerful new approach to compressed environment imaging, encoding only the most essential features using a domain-trained generative model. By operating in a semantic latent space, LSI prioritizes meaning over raw pixels, making it ideal for perception-driven tasks. Its compatibility with minimal hardware opens the door to ultra-fast, low-power, and privacy-preserving imaging systems. This makes LSI particularly promising for edge devices and real-time applications where traditional imaging would be too resource-intensive. For more details, comparisons, and further discussions, please see the full paper and the links below. Thank you.